We have come to a really exciting point in the quarter because we're going to start to see how all of the hardware modules that we've been creating are going to fit together to be able to execute the instructions that we want to be able to execute. So in this lab, we're going to combine the program counter, which you've already created, the program, which gets generated from RATSIM based upon the assembly code you type, the register file, which we created in our memory lab, the ALU, which created in the ALU lab, and this lab we're going to add on the flag registers and the control unit, and we're going to connect all of those units together, as I'm showing in the mouse here, to create a bare bones computer. Now there is some other hardware, the stack pointer, which we have not yet made, and the scratch RAM, which we have made, that we're not going to connect in this lab. So you don't need to worry about the stack pointer or the scratch RAM. We're going to be connecting all of the other components. Now let me orient you a little bit more to this diagram. Everything in a bold black box is an input or output to the overall CPU. So if you put a big box around this entire picture and change it into a black box, the bold items are what you would see as the inputs and outputs of the overall overarching entity. Interrupt stands for an interrupt input, which we'll be using later on this quarter. Reset is just an overall reset to start the machine over. Clock is obviously the clock. Import is coming as data from an input device such as a keyboard. I/O strobe is allowing to output to an output peripheral. Output is data going out to an output peripheral like a VGA monitor, and the port ID identifies which peripheral to use. We won't be using all of these things quite yet, like the interrupt, but we will start putting these to use in this lab. Okay, the other thing in this diagram to note is everything with the little price tag looking symbol is a control signal. So this iSet, iClear, SPLoad, SPMux select, ALU op, all these over here are control signals. And most of the control signals are set by the control unit. So you can see the output of the control unit has all of these signals. And they're grouped really nicely. As you can see, the ALU has two control signals, ALU operation select and ALU op Y select it's called, and ALU select, which is 4 bits. And then if you look at the ALU, you'll see that these are the control signals that are inputs for the ALU. So ALU select comes into the ALU, and ALU op Y select goes into this MUX. And so you can think of these things as being connected. This ALU op select is this ALU op select down here. So it's coming as an output from the control unit to be an input to this MUX. Just like this ALU select here is an output of the control unit going to the ALU. So it's really nice that these are grouped like that. So as you can see, all of these control signals, SCR write, SCR address select, are all referring to the scratch RAM, which is down here, and you can see all those control signals related to the scratch RAM down here. Again, outputs of the control unit and inputs of the scratch RAM. We're not using the scratch RAM in this lab, so you don't even need to worry about those, but I'm just trying to give you the idea of the grouping. So that's pretty cool. The other nice thing about this diagram is everything that's not in this price tag looking signal is known as the data path. So everything else like the count, the address, the instruction, these are just bits flowing throughout the machine. That's often known as the data path. They're separate from control signals because control signals are coming from the control unit telling each of these units what to do with the data path. So the control unit needs to tell the PC if it needs to increment, and if it tells the PC to increment, then the output of the PC is going to be whatever it was plus 1. If it told the PC to load an input from the immediate value, then it would say PC load is 1, and the immediate value would be PC mux select would get 1, 0, and therefore it would change the PC count appropriately. So think of the control signals as commands to tell each of these hardware units, or rather modules, what to do to the data that they have. Okay, so the big part of what we need to understand right now is how does this control unit work? So if you think back to 133, how did you make a control unit or something that controlled something? I'm hoping you're thinking of the term FSM. Yes, a finite state machine, all that is a simple controller. So all this control unit is one big finite state machine. The states for our architecture for the microcontroller are actually very simple. So let me pull up the state diagram. It's very simple. There's only 3 states in our architecture. There is the initialization state. And how you get to the initialization state is through the reset. So remember that reset is one of those inputs to our overall microcontroller. And if reset is 1, it's an asynchronous reset. It'll just put us back in the initialization state. What that's going to do is it's going to reset our program counter back to the beginning, which in our case is probably 1, and start the program over again. Once we get out of the initialization state, we go into what's known as a fetch state. All that happens in the fetch state is fetching the instruction from the program that's at the address given to us in the program counter. So if the program counter is 1, in the fetch state, what we're going to be doing is fetching the instruction in the program at address 1. Once we get that instruction, we are going to move into the execute state. So now let's say our first instruction was a move instruction. Once we're in the execute state, we're going to go ahead and be able to set our control signals appropriately to make that move occur in our CPU. Once that move occurs, then we can go back and fetch the next instruction. So our program counter will get incremented, and we'll fetch the next instruction at address 2. Once we get the instruction at address 2, we can go ahead and execute it. And once we're done executing it, we go back and fetch the next instruction. And as you can see, this will just go on and on and on and on and on forever and ever and ever unless we get an asynchronous reset to put us back to the beginning and start all over again. So it's a pretty simple state diagram. The init state is very, very simple, which I will show you because all it's doing is resetting the program counter. The fetch state is really, really simple because all it's doing is fetching the instruction at the given address of the program counter. And so that's the same for everything, every single instruction. The execute is where things get really interesting because to do a move or to do an AND or to do an or to do a branch, these are all different things that have to happen. So in order to do those different things, we need to give different commands in the execute state depending upon which instruction we want to use. So I'm going to go over an example that shows you how we go through this state diagram in a simple program. Alright, so the example we're going to do is this very short program where we're going to move R10 0xAB, move R11 0x11, and sub R10 R11. I'm actually going to also put the .org statement or .csig.org up here so we can remember where the origin of our program is, which in this case will be 01, which means that the move instruction will be located at address 1, next move will be at address 2, and the sub would be at address 3. Okay, so what I have here is what you might be looking at in your iSim if you were going to test this after you connect everything. But I'm showing it to you in terms of how this fetch and execute stuff works. So think of the clock as going down and then up. So at every column edge in my Excel window is a rising edge of the clock. So think of it going over, down, over, up, over, down, over, up, and every one of these column edges is my rising edge. At the rising edge, I'm going to change states. So I start off in the init state, which is where I start my computer. Remember, the state machine is just init first. At the rising edge of the clock, we're going to go into the fetch state. So PS means present state. When the fetch is done, at the next rising edge we go into execute, at the next rising edge we go into fetch, next rising edge we go execute, etc., 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 forever and ever and ever, unless we get another reset signal. Now recall there are two different reset signals. There's the reset signal that's coming in to the overall CPU, and then there's the reset signal that is a control signal coming out of the control unit. So here I've just listed a couple of different signals that are both control signals and data path signals that we're going to look at and see how they change in this timing diagram. Okay, so what I've done here is I've highlighted the control signals in yellow. So these are all signals that are coming out of the control unit as dictating to the rest of the machine, what do you need to do? And the other signals are all just data path signals. So in the init state, the input reset is 1, and I am going to then go ahead and set the control unit would set the reset signal to 1, which is an output reset of the control unit, to tell all the other modules to go ahead and reset their states. Now the PC is going to be initialized to whatever you initialized it to when you wrote your program counter module using the : operator. I told most of you to initialize it to 1 because our RATSIM likes to start at 1 instead of 0. So the initial value depends on whatever you put in your VHDL code. So that's going to be a 1 in my case. The instruction is going to be whatever instruction is at the program counter. So we know that the instruction is going to be the move instruction. So we're going to be able to get the move instruction to come out. Now what you would actually see in ISIM is the assembly code, or rather the machine code that represents that assembly instruction. So you wouldn't actually see the word move, you would see the 18-bit code that this represents. PC increment is going to be 0 in the init state because we're not incrementing anything, we're just resetting the system. Okay, so I could list every single signal that's in that architecture diagram down the left-hand side and fill out what it would be for every state, but right now I'm just focusing on these few just so you can start getting an idea of what's going on in the fetch versus execute states. Okay, so in the fetch state, what's going to happen is I'm going to fetch the instruction at the program counter specified by the previous cycle PC. So I already have a 1. I know that's going to be a move, so I'm going to fetch the move instruction. The fetch state is not going to change the program counter. It's going to stay a 1. And my reset is not going to be a 1 anymore because I'm not resetting anymore. But I'm going to go ahead and increment my program counter. So what happens in the execute state is, because I said PC inc would be 1, in the execute state the PC is going to become a 2 because I had to increment the PC and it became a 1 and then a 2. My instruction is still going to be the instruction at the address of the previous cycle because it still has the instruction from that address, and my reset is still a 0. And in the execute state of a move, I'm going to not increment the PC because I incremented it in the fetch. So when I want to do the next instruction, the next fetch, what happens is, because I didn't increment the PC, my PC is going to stay the same. Now I'm going to fetch the instruction at the address 2. So I fetch the instruction of the program counter value in the previous cycle, because you have to think of, at this rising edge, what is everything that's before that edge that's going to be used to change something after the edge. So if my program counter is 2 in the execute, my instruction is going to be whatever is at address 2. So it's the next move. It's the move R11. And my PC inc in every fetch state is going to be a 1. My reset's going to be a 0. So from now on out, my reset is always 0. The only time reset is a 1 is if I'm in the init state. So the PC is going to get incremented now because it said, okay, go ahead and increment. Its current value is 2, so at the rising edge it's going to become a 3. The instruction that I still have is the one with the PC from the previous cycle, so that's the move R11. PC inc is 0 because I increment on the fetch instead of the execute. And I continue. So now I'm on the fetch. I'm going to fetch the instruction at address 3, which is the sub. The PC is not going to change because I didn't increment it. And then my PC inc is going to be 1 because I'm going to always increment the PC on the fetch. So I can just fill that in. PC inc is always going to be 1 in the fetch state no matter what instruction I'm executing. Then in the execute state here, I have still the sub instruction because the PC from the previous cycle is 3. I'm not incrementing the PC, and because I had set PC inc to 1 from the fetch state, it will increment from 3 to 4. And I execute the sub, and then because PC inc is because the PC is 4. In my next fetch, I'm going to get the instruction that's at address 4. Well, nothing is at address 4, so I'm just going to get zeros because I didn't put anything else in memory, so nothing else is going to come up. It's just going to go to address 4 and get zeros. The PC remains the same because I did not increment it. And then I'm going to go ahead and increment the PC because PC inc is 1 in the fetch state. And there's nothing there at address 4, so this remains 0. And 0 for the increment. Okay, so we're going to go through and fill out more of this table, but right now, take-home message is that we're always going to increment in every fetch state, no matter what instruction it is, and that anything you change in one state is going to be dependent upon the values in the previous state. So for example, when PC inc is 1 in the fetch state, you're going to see the increment occur in the next execute state. So because it's 1 here, it went from 1 to 2. Because it's 1 here, it went from 2 to 3. Also, when you are getting the instruction, it depends upon the current value of the PC. So the value just before the clock edge. So this move is dependent upon this address 1, this move is dependent upon that address 1, this move is dependent upon address 2, etc., etc. So you always have to see what's going on in the previous state to see how it's going to alter the next state.